Cool. Okay, so we're gonna jump right into it. As a reminder, I hope you all know this by now, but your exam is on Wednesday. It's at your normal scheduled class time. It's set up exactly like it was last time. So you come in at your scheduled class, they'll split you into two groups. Someone will monitor the half that your professor can't. For Liao's class, that'll be me. For Dr. O'Neill's class, I don't know who that's gonna be, but it's gonna be exactly like last time. I'm going to close the chat, which means if you guys have a question, say it out loud, interrupt me. I'll open it at the end of every section, but it's just blocking like most of the screen. But yes. So yeah, interrupt me. Feel free. I don't care. So we're gonna jump right into content review. And the first subject that we went over, which was a long ass time ago, was centroids, right? So this one I kind of wanted to check up on a lot. So centroids won't be a standalone question. They're going to be a question they're going to be incorporated into another question, essentially. So you really only use centroids when there's a distributed load. So yeah. So as a reminder, centroids like conceptually are a representation of the center of area, which means kind of like center of mass is talking about the distribution of mass. Centroids are discussing the distribution of space, or like the actual body of the the structure you're looking at. So conceptually, I don't know how many of you are sitting in a spinny chair right now, but I know everyone's done this. So if you were to spin in your chair, and your cameras are all off, so I absolutely won't judge you if you do that. If you spin in your chair, right, and you put your legs out in front of you, you spin a lot slower, right? If you have your legs tucked in like under you, you spin a lot faster. And that is because of the centroid and how that affects the moment about like the spinny part of the chair, right? So that's so where your legs are changes the center of area on your body, right? So if the chair is rotating about basically under your butt, but the center of area when your legs is sticking out is like at your knees or something, that's going to change how fast you spin about that moment. So this is the table that you get in the reference card. And I kind of basically went through each one and figured out kind of a description on how to go through it. So in this leftmost column, shape is you break the entire figure up into smaller pieces that are like recognizable to you. So most commonly because this is with a distributed load, it'll be either triangles or rectangles. So in reality, you'll probably only have a triangle and a rectangle in the shape section. And then for the area, you just calculate literally the area of the shape. So the magnitude of the force is the vertical part, and the area that it's acting over is the horizontal. And then you just do base times height, or 1/2 base times height, and that's the area. It won't happen like this probably on the exam because it's for distributed loads, but if for some reason they gave you a centroids question, which I absolutely have never seen or heard of before, you can use the area column to indicate whether it's something cut out of a shape or if it's an added piece of the shape. But if it's for a distributed loads calculation, these will both be positive. Every value in A will be positive. And then at the end, you're going to sum all of the values in this column. And then moving on to x tilde, this x tilde and y tilde are the really only complicated parts of this chart, right? So super easy to find the shape, super easy to find the area, and then super easy to multiply two things together. X tilde and y tilde are where people mess it up. So x tilde, you use that card, the white one that has all of the shapes on it. I don't remember what it's written as, but it's the geometry sheet basically. And each shape has a description of the x position of the centroid and the y position of the centroid. Basically, you just follow that card to find the centroid on the shape, but then you have to remember that since we're taking a moment, you really want the perpendicular distance about the axis. So here, my is the moment about the y-axis, right? So you need to find the distance in the x direction, which is why you use x tilde. But x tilde has to be measured from the y-axis or it's not the perpendicular distance. So that's the big piece that people remember, or don't remember. So there's that. And then you just multiply ax, or a and x tilde, and then y and x tilde, or a and y tilde, and then you get these two. And then to find the location of the centroid, you just plug in the summed values of these columns into these equations. But again, that probably won't be like that on the exam. You're probably just going to have to know where it falls on a distributed load, which is a lot easier than plugging it into these equations. And then, so, I mean, if you were to get this question, my biggest tip is to logic check your answer, because on the quiz, there were some people who put it that the area or center of area was not on the shape, and that's not possible. Like, it can be in the cutout, but it won't be like completely off the shape. So that's just important, is just to logic check your answer. So distributed loads, again, won't be a standalone question. It'll be used, oh wait, actually, does anyone have a question on centroids yet? Likely not, because it's not really that important.
Good so far.
Sweet. Okay, so for the distributed load stuff, again, won't be a standalone question. You're going to have it built into a structure, kind of like you saw in this last quiz. There was a distributed load on the side of the frame. So that's kind of how you're going to see distributed loads. Basically, they're just a point load broken up over an area. So to get it back from a distributed load to a point load, you have to consider the magnitude that it's representing and the location that it would fall on. So for the magnitude, you would multiply the magnitude of the distributed load times the distance that it acts over. So the magnitude of the distributed load is the one that's written as newtons per meter or pounds per foot. So that's the number that you multiply by the distance that it acts over. And then for the location, the point load would act on the centroid of the shape that the distributed load is. So if you have a triangular one, the point load that represents the distributed load is going to act a third from the base of the right angle in that triangle, right? So that's just something to remember. That's really the only reason you need centroids. So kind of talking about what we were going into here with the whole breaking up the shape into different shapes. There's something called a composite distributed load, which is basically a combination of two geometrically common shapes. So you've seen that a lot with a triangle or triangular distributed load sitting on top of a rectangular distributed load. So basically you do the same steps, you just separate it and solve it as two separate distributed loads. The one thing to remember is that if it's a triangle sitting on top of a rectangle, you have to make sure that you're doing the rectangle as one magnitude, and then for the triangle, you're subtracting the max from the value that's at the rectangle. I think I have an example later on that I'll point this out again, but you have to make sure that you're using the right magnitudes, basically. And I guess the hardest part with the distributed loads thing is figuring out when you're supposed to consolidate the load. So really, you're going to do it twice in some cases. So if you're finding the external forces on a frame or the reaction forces somewhere, you have to solve or consolidate it into the point load right away, which means when you're solving for something that you haven't cut the member, you consolidate it right away. But the tricky part is if where you cut the member crosses through a distributed load, you have to consider the fact that that distributed load is acting on the cut. So that's going to change your distance that it acts over, because by cutting a member, you are essentially shortening the distance that it's acting over. So then again, we'll go over this when we have an actual like example problem in front of us, but this is probably the trickiest part and the part that people will lose points on in terms of distributed loads. So any questions on that? I know this stuff was a long time ago, but we've kind of been using it. Guess not. All right, so jumping into trusses, this might be a standalone question. Don't know for sure. It's not exactly like the last exam where they told you you have 2 3D and 1 2D, so go practice. So you could have any kind of question that focuses along the main structures that we've been talking about. So trusses is one of them. So this sounds dumb, but trusses are bridge structures. So if it looks like a bridge, it's a truss. So that's the biggest way to distinguish between a truss and a frame, is that frames don't look like bridges. Trusses do. So the question for a truss problem would look something along the lines of find the internal forces in members and then list of members, right? So there's 2 different approaches to doing that. If we'll go over how to pick which method to use later on, but the methods are method of joints and method of sections. You guys have used this twice, so I'm sure these are pretty familiar, but I'm going to go over it anyway. So solving for method of joints, right? You pick one joint, which is where the members meet, and you essentially cut every member that meets at that joint in half, right? So this member, and this member all meet at that joint, so they were all cut. You guys can see my cursor, right? I've been sitting here pointing.
Yeah.
All right,
You're good.
All right, cool. I just realized that I had no idea if you guys could see that. So, yeah. So all of these members meet at that joint, so you've cut all of them, exposing the internal forces, right? So you only need to solve for external forces, really, if you are cutting a corner joint. So if you had like a pin here or something, and you were isolating this joint at this corner for the method, if you look under the method of sections 1, if you were isolating the top right corner and you had a pin here, you would need to find the external forces, but you don't always need to for method of joints, which is why it's nice. So you pick one joint, cut everything around it, which exposes the internal forces in those members, right? And then basically you just use your equilibrium equations. So because they all meet at this one point, by definition, it's a concurrent system. So you can only use some of the forces in the X direction and some of the forces in the Y direction, which means you can't take a moment, but usually it's pretty simple. And then what's nice is if it's asking for forces at, or that meet at the neighboring joint or something, this unknown here will transfer to that joint over here. So that's what's nice about the internal force calculations, is that they hop from member to member. And you'll see that pretty regularly going forward. So that's method of joints. Any question on method of joints?
So what are we actually like if we got a method of joints problem, what would we actually be like solving for? Like just one of the forces in one of the members there, or
So likely
or like
what we'll be solving for is, we kind of go into this a little bit later, but for method of joints, it's going to be a question that asks you for almost all of the internal forces in the structure, right? So if you're asked for 3 or 4 internal forces, right, and they're all somewhat related to each other, where you could cut through the truss through the members, you use method of sections. But if there's no way to relate the unknowns that they're asking you for, you would have to use method of joints and then hop from joint to joint.
Okay, got it.
All right, cool. And then for method of sections, kind of like what I said like just now, you are going to be asked for a certain list of internal forces that you can relate to one another by proximity, right? So if I was asked for the internal force in this member, the diagonal member, and the bottom member, I can cut right through all of those and say, I don't give a half a crap about anything going on in here. So I'm just going to not expose those unknowns and then cut it here, only expose these, and then solve for those using the entire side of the member or of the body, right? So again, you would have to, for this one, you would have to solve for the external forces because you're now considering this whole body instead of just that one joint. Because here, unless it's that corner joint, it won't have any external forces on it. But over here, since you're looking at the entire side of the truss, you would have to consider those external forces and any loads that are hanging off of the bottom of it. Oh, shit. But, yes, so once you find the external forces, then you cut through the ones that they're asking for, right? And you can only cut through 3 that you don't know, which is why you should probably look for zero force members at some point, because if you need to cut through 4, one of them is likely a zero force member, or you're looking at the wrong cut. So there's that. And then just make sure that your cut is completely separating the 2 bridges. So you can't like cut around here or something like that. So like you wouldn't be able to fully separate the bridge if you just kind of cut through this. But if you cut straight through, you can actually pull the 2 pieces apart. That's how you know you cut it right. And then once you expose these forces, you basically solve it with a concurrent or non-concurrent force system, which means you have all 3 equations. So some of the forces in the x, some of the forces in the y, and the moment equation. So real quick, if I was going to solve for these 3 unknowns, what would my first step be? Anyone know?
Probably to sum forces in the y, or I mean,
You'd probably want to take a moment about that one point where those 2 are both about to meet at the same point, because it would cancel those out and you can find the bottom one there.
Okay, those are both valid options. There's actually 3 ways that you can do it. So you can say that I know that this is the only one, as it's written right now, this is the only force that I don't know going in the y direction, right? Which means I can take some of the forces in the y and say that I know this is equal to whatever combination my external forces are. So that's fair. You're allowed to do that. You can also say I know that this one and this one are meeting at some point over here. You can take a moment about this point and get this bottom one down here. You can also say that I know that this one and this one are meeting at this point, so you can take a moment about this point and solve for that one. So there's, basically you just solved the whole thing. So there's that. Super cool. Any questions?
Yeah, I have one question. Will we go over how to identify the zero force members?
We can. I just realized that I haven't put it in here yet, but we can do that towards the end. Unless you wanted to do it now. We can do it now. How about that? How about we do it now? So there's 2 cases for a zero force member. So either you have 2 members that meet at a joint and there are no external forces at that joint, which means as it's drawn here, that's what's happening right here, right? So because this member and this member are both meeting at that joint and there's no external forces, that would be there. That would mean that both of these are zero force members, right? So that's the first condition. 2 members meeting at one joint with no external forces acting on it. Then both of them are zero force members. The other option is you have 3 members at one joint. 2 of them have to be in a straight line, right? So if you look at this joint right here, right? These 2 joints that meet, or these 2 members that meet at this joint are collinear, which means that they're in a straight line with each other. That means that the one that's not collinear, so basically this one, the one that comes off of that straight line, is the one that is a zero force member. But again, that's only true if there are no loads at that joint. So this joint, essentially, if there's something hanging from it, that won't work. But if there's not, so as it's drawn now, basically, this is a zero force member. Does that make sense?
Yeah, it does.
All right. Anyone have questions?
if there's a force like on that joint you were just pointing out, if there's a force like pushing down from the top, would that not affect it at all? Like if there's like a force on like that member, but it's not specifically on like that joint.
Right. So that's exactly true. So if there is a force pushing down on this top piece right here, it would not affect this joint, because if there's nothing on this joint, then that means this is zero force member. So essentially all that would mean is that this force that's hanging down here is acting 100% through this and this member. None of it actually makes it through this member. So that's a
Okay.
very good point to bring up, that if you're looking at method of sections, or if you're looking at this like the 3-member rule to find zero force members, you have to make sure that your force is going 100% through the joint, not through one of the members by like association. That was a good
Okay. Cool. Yeah, I think I've made that mistake before. So
call. I have made that mistake.
Same here.
All right, cool. So is that, anyone have any other questions?
Yeah, I have a question. So for the top right corner of that method of sections picture, you were saying like if there was no external forces, then those 2 members would be zero force members.
Yes.
What if they're like, if that corner is like a pin attached to a wall and there's reaction forces, do those count? Or is it just like external loads that count for zero force members?
No, so that would count. So if the bridge was meeting some kind of land like down here, then there would be no external forces here. But if you're right, so if this is the point where it meets land, then there would be external forces here, which means these cannot be 100% determined that they're zero force members.
Okay, thank you.
For sure. Anyone else? All right, so moving on to frames. So frames are kind of, no, they're not really, not at all. So they're going to be standalone question. They'll be combined with internal forces, probably. So we'll go over that in a bit, but if you get a frames question, it'll probably be a frames 2 style question, which means you're going to have to hop from free body diagram to free body diagram. So we'll go over that in a bit. So by definition, frames are structures where members are held together by pins, and to solve the structure, you're going to pull those pins out. So eventually those pins will be removed. So to identify a frame, it'll be a complex structure that doesn't look like a bridge. It sounds really stupid, but to this day, this is how I remember it. One's a bridge, one's not a bridge. So there's that. So when you're looking at evaluating a frame structure, and I'm going to talk about how to do it with without the internal forces component, because that's in the next slide. So this is a question that's like, find the pin reactions at this pin and this pin. And so that's going to be a frames question. So basically your first step is to solve for any external forces you care about, if you can. Second step is to remove every pin and separate it into individual members, right? And once you've separated it into the individual members, you want to draw a free body diagram of each member on the whole body. So an important thing to remember is 2 force members, right? Because those are just going to be a single unknown, which makes it a lot easier than breaking it up into 2 unknowns. So with 2 force members, again, to identify them, any kind of member can be any shape, but the only forces acting on that member are the pin reactions. So if there's a structure that doesn't have any kind of applied load other than the pin reactions, that's a 2 force member, and you can just approximate it as 1 force in the direction of like one joint to the other joint. So I think there's a problem with a 2 force member in it in the future, and I'll show you a little bit more about it there. So once you've identified 2 force members, you want to draw the reactions at the pins, and each pin has a vertical and horizontal reaction, right? So it's kind of a lot like a pin as a support structure where you have an unknown in the X and in the Y, because it can still rotate technically. That's exactly the same thing for this. So you have every time you pull a pin, you expose a vertical and horizontal component. So when you're drawing up free body diagrams for a frames problem, every time you pull a pin, you're going to have, say I pull pin C, I'm going to have a CX and a CY on one of my bodies and a CX and CY on the other body. Because the member is not moving at that pin, you have to make sure that you are, oh, okay, yeah, I just let them in. Thanks, Anna. But yeah, so because you are, your body is not moving, the combined or the overall force at each pin has to be 0, which is why when you separate it into multiple free body diagrams, the forces that happen on each of those free body diagrams has to be equal in magnitude and opposite in direction of each other. Oh, well, I was supposed to ask you guys why that's true, but I just explained it. So essentially it stems from the fact that the body's not moving, and that's why they are opposite in direction. Cool. Yeah, no, for the record, I can't see the chat, but I think it kind of sends me a notification when people are typing, or I mean, when something comes through. So once you've drawn your free body diagrams for each one, you kind of just have to jump in and start solving for your unknowns. Up here where I said it's going to be a frames 2 style question, that kind of comes from the fact that very few, I would almost say that none of your individual member free body diagrams will only have 3 unknowns on it. They'll have more than that, which means you're going to have to kind of see how those unknowns relate to each other. But what's nice about it is you can, because so many of them will end up on multiple free body diagrams, that's a lot easier to simplify the problem, basically. So you can take the moment about one point, find the reaction at another point, and then that is what gets translated to another free body diagram, which eliminates unknown on both of them, essentially. So any questions about that?
Wait, my phone's almost done.
Um,
82.
Oh,
so, like for between frames and trusses, are we probably gonna get like one of each of these on the
Yeah,
exam?
sure.
Or
you might, and Steven, your mic is very on, but yes, you get one of each. So it's important to figure out which one's which. And again, the only thing separating them is pretty much what they look like. So a truss will be a bridge, a frame will be something that's not a bridge.
Right. Okay. And do you know how many questions? I know this is probably like later discussion, but I mean, is it going to be like 3 again, or
I was told there's
it's
4.
going to be like 4? Okay. Okay. Cool.
Yeah.
Thank you.
Yeah, no problem. So I would assume that because it's 4 questions, one of them is going to be pretty short and like relatively quick. I don't know what that would look like. I don't remember from when I took it, but yeah, one of them I'm sure is going to be relatively quick. But yeah, so any other questions about frames before I move on? The important thing is to be comfortable with the fact that you're going to have things that aren't 3 unknowns only, which just means you're going to have to translate or find one and move it to the other bodies that exist within your system. So anyone else have questions? Yes, no, maybe? Cool. Moving right along to internal forces. Again, this might not be, it could be its own question, probably won't be because they only have a certain number of questions they can ask to test your knowledge about the whole thing. So they might ask for, with a frames question, they might ask for the forces in the pins at one of the pins and then the internal forces somewhere near that. But internal forces essentially are the forces that you expose by cutting a member to see what's happening inside of it, right? So internal forces conceptually are the forces that the actual structure you're looking at exerts to try to not break, right? So if you have a force pushing on, so this is our nice little body, the little gray box. So if you have a force pushing up here and then up here, right, you're kind of bending the member a little bit, which means that whatever's going on inside of this structure is trying to make sure it doesn't break. So similarly, if I have a force pulling outwards on each side, this member is going to try to be pulled apart, which means something going on inside this member is going to try to keep it from being pulled apart, right? Same thing with the moment, it's going to cause it to try to bend, blah, blah, blah. Does that make sense kind of conceptually? Silence is a yes.
Yes.
So there's three forces that you expose. The shear force is the one that goes parallel to the surface. The normal force is the one that's normal to the surface. And the internal moment is a moment that rotates about the exposed surface, right? So technically, when we learned it, there are positive conventions, just so you kind of remember that the forces should be equal and opposite. Because again, if I were to reconnect this cut or this half with the other half, it won't move, because in statics it's not breaking, right? So all of these forces only exist when I cut it. So if I were to put the other half right here, the arrows should point in the exact opposite direction. So the shear force should point up, the normal force should point to the left, and the moment should be clockwise. So the conventions really only exist to make sure that you remember that. So for the shear force, positive is the one that causes clockwise rotation of the body. So if I was to push down on this side, this whole rectangle would spin clockwise. The normal force is always pointing away from the surface, and the moment is causing a concave up bending, because if I rotate this side up, it's going to bend it into a U shape, which is concave up. So you don't necessarily have to follow those conventions. It's recommended that you do, but yeah, you don't necessarily have to. It's just to make sure that you're being consistent with the equal and opposite thing. So when you solve for internal forces, you're exposing 3 unknowns, right? Which is the maximum number of unknowns you can do if you're looking at one body, which you're going to be doing in an internal forces problem. So because you're only looking at one body, you can only expose 3 unknowns, which means every other force that's acting on this body has to be known. So if there's a vertical and a horizontal reaction happening here, say this body's like pinned somewhere, if there's a reaction force here, you have to know those before you cut it. So essentially what I'm saying is you're going to have to solve for the external forces before any forces or reactions before you cut the member, right? Because you're exposing 3 unknowns, which is the maximum. Once all of those are found, you can cut the member, draw a free body diagram for one side. It's up to you which side you pick. I usually pick the side with the least stuff on it because that's less math, which means less mistakes. But it's your call. If you want to be extra and do it on the complicated side, no one's stopping you. Again, just draw the forces, and then it's really just an equilibrium problem, right? Because you'll have one unknown in the y direction, which just means some of the forces in the y, you solve for that. One unknown in the x direction is your normal force, solve for x, or some of the forces in the x direction, solve for normal. And then you take a moment about this point, about your cut. So you do this moment plus force times distance on every other moment acting on the body, right? And then you solve for that. And then because, like I said, when you cut it, you expose it in both sides, right? So if I had the other body right here, the forces would be over here. If my convention was right, it would be down on this side, but up on the other side, which means it's very important that in your answer, you specify which cut you looked at, or which side of the body you looked at, because it'll tell you, or it'll tell them really, whether your direction is right. So the only other thing that I wanted to make sure you remember is this is the part where you consider when you find the point load for the distributed loads. So if there was a distributed load going over this entire body, right, I would need to consolidate it first to figure out what my pin reactions were at this corner. But once I cut it, I only look at the part of the distributed load acting on this cut. So you basically consolidate it twice. All right. So any questions?
Oh yeah, does the moment always have to be concave up?
That's kind of what I was saying earlier. It doesn't have to be, but just remember that when you draw it, it'll be equal and opposite on each member. So it doesn't have to be concave up, but it'll be the opposite direction on the other side. And the only reason that these conventions exist is because they'll be true regardless of which side of the cut you're looking at, right? So the shear force will always be down if you're looking at this side, because if I push down, it spins it clockwise. If I'm looking at, say this was the side of the other one, if I push it up, that spins this clockwise. So all of these conventions just exist to make sure that you're saving yourself from mistakes by forgetting the equal and opposite thing. But no, technically you don't have to do that.
Okay.
That's a good question. Anyone else?
Will we be doing an example of this later?
I don't have any full problems set up, but we're kind of going to talk one through. If you guys want to stay later, I can stay, depending on what time we finish, I can stay a little bit later and we can do one. But yeah. I'm sorry, was that the last question? Yes, no, maybe? All right, cool. So moving on to cables, there wasn't a cables question on the quiz, which means you probably didn't have much practice with it. So this is probably one of the sections that you want to study because it could very easily be a standalone question, right? I kind of doubt personally that they would give you a truss question and a cables question, but I could be totally wrong. So don't take my word for it, but in my head, it's testing the same exact knowledge. So maybe it won't happen. I don't know.
Let's
So
hope
again,
so. Knock on wood.
well, yes, either that or like you could hope it would happen because you're really good at method of joints and method of sections. So
Fair.
depends on who's asking. So this could easily be a standalone question because there's really very few things that could happen in conjunction with cables. So cables logically are structures that are used to hang things, right? So basically what's going to happen is you're going to have a series of cables that are, or technically it's all one cable, but you're going to have a series of like sections of this cable connecting two sides of something. And since we're in kind of like the elementary part of explaining cables, these two will be at the same height because that makes it super easy to solve them. Kind of touched on that in class, but yeah. So basically what's going to happen is you're going to have two sides connected on across some kind of plan, I don't know. And then there will be given loads at the joints that kind of indicate a change in direction of the cables, right? So it could be a stoplight, that's a common one. It could just be some box hanging, but it'll be something hanging, right? And they'll give you either the mass or the weight. So if they give you the mass, which they've done historically pretty frequently, if they give you the mass, make sure that you multiply it by 9.81 to get to the weight. But there's a couple unique things about cables that make them kind of weird. Cables are always in tension because if I'm using a cable, it's to suspend something, right? So no one's ever pushing on a rope to hopefully support themselves. I mean, if you are, good luck. But generally, if you're using a cable, it's to hold something in tension, right? So we're going to assume that. So that's one thing. So all of your arrows in your exposed like tensions should be pointing away from the actual member. In terms of evaluating it, they're very similar to trusses, right? You have your method of joints and your method of sections. And again, deciding which one to use is kind of pretty similar to trusses, right? So if they ask for the tension in each of the cables, you have to use method of joints because then you can just hop from one to the other and it's fairly simple, right? So you isolate the joint, you keep the load that's on it, but you expose the two tensions, and then it's just the sum of the forces in the x direction and y direction. And you would have to start at one of the ones that has the external forces, because otherwise you wouldn't know the unknown x direction. For method of sections, it would just be if they're asking you for one of the tensions, so you kind of just cut it here, or cut it, I'm assuming they're asking for this one, so you cut it through the one that they're asking for, and then you have essentially a bunch of knowns and givens, and then just that one unknown. So again, this is a concurrent system, this is non-concurrent, so you have 2 equations here, 3 equations here, and you solve it essentially exactly like a truss. So does anyone have any questions on that? I kind of went through it a little quicker because it's basically the same content as trusses.
I just got a real quick question.
Yeah,
So
what's
I
up?
was going over some of the problems that he had posted, and he solved one of them by method of inspection. Like, what's the difference? Or
So
we
inspection just means that you don't really have to do actual math to find the answer. That's a really good point. If there's something like, so it's at some point it'll be really, really obvious that one of the forces equals some value, right? So that's pretty common, especially in trusses, right? So if there is a pin on this side and a roller on the other side, and you're looking at external forces, right? So none of these arrows would be here. So if there's a pin on one and a roller on the other, and nothing hanging off of it, by inspection, your X reaction at this pin would be 0 because there's nothing restricting the X in this side. So you don't actually have to set up the equation and do all the math just to say that I know this is 0 right off the bat.
okay.
So method of inspection is basically just a shortcut that says I didn't want to write out all the math because I could tell right away by looking at it. That being said, if you don't see it right away, you can absolutely write out the equations. There's nothing saying you can't do that. It's just a matter of how comfortable you are with saying, I know for a fact that this is this value.
Okay, and one more thing, sorry. Would
Yeah.
it be wrong to assume, like, let's say in that method of sections, let's just assume that the cable, if you were to complete the cable to the left, both ends are basically even at the same point. Would it be wrong to assume that the force in the X direction are both 0? I think that's what the problems were saying. I just don't want to get mixed up if
So it's weird with cables because you're talking about the reaction forces, right?
yeah.
So your reaction forces are always going to be parallel to the member that first comes off of the wall. Because if I'm pulling on a wall, right, the wall is pushing exactly opposite or pulling exactly opposite of it, right? Because if it's not moving, it has to be that case. So you could technically break it up into a vertical and horizontal, but that doesn't necessarily help you because you know it's going in the direction of the cable.
Okay.
Did that answer your question?
Yeah. No, I'm good. Thank you.
Cool. Anyone else?
How much does a question change when like both ends of the cables are at different heights?
It becomes a lot more complicated to find the external forces, I think. I don't actually know because we don't do it in this class. And I'm a bio, so I don't ever look at cables again. So, terrible answer.
Okay, gotcha.
Question.
Yeah, I mean, I'm bio too, so thankfully.
Same. So I know Dr. Liao talked about it for like a solid 7 seconds at the end of one of her classes, but basically just know that it'll always be the same height in this class.
All right, cool.
Cool.
Thank you.
Anyone else? All good questions, guys. Really good. All right, cool. Moving on. Pulleys. Again, this won't be a standalone question because this would be probably way too easy unless this is the fast question that they're talking about. So, I don't know. I would study it, but it's fairly simple and relatively quick. So, again, it'll probably be used in another type of evaluation, which is exactly like it's written right here. I hope you guys remember this problem. I actually love this problem. But anyway, pulleys have two functions essentially. So either they can translate the direction of a load, right? Which means kind of what's happening here. The load is hanging down, but the pulley is essentially making it pull on this member to the right, right? So that's kind of what it means by translating the load. Alternatively, it can reduce the necessary applied load to move some kind of weight. So here's this weight, and it ends up being divided a bunch of times to actually reduce this value needed to lift that. So that's kind of the two applications. And you kind of solve them entirely differently. So if you're looking at one that translates the load, you don't actually really deal too much with the pulley, other than you know that there's a pin that holds the pulley where it's at. So there's a force here and a force here, like at the center of the pulley. And then also this weight is exactly translated to this body to the right. So a couple things looking at this picture. I know it's kind of small, and I kind of regret making it this small, but looking at this is a frames problem, right? So you pull all the pins, separate everything. This member right here is a 2-force member, right? I hope you guys remember that. But the only things that are happening on this member are the reaction forces at the pin, which means I can approximate it as one force that connects these two pins, right? So that's one simplification. I can also get rid of this pulley entirely by saying I know that the reaction forces at the pin that holds the pulley on here are the weight times the radius of the pulley. Whatever it's like the load is times the radius of the pulley. And that's in the Y direction and the X direction, right? So that's another simplification. The only thing to consider is that when you get rid of this pulley, you have to make sure that this force is happening everywhere it has to happen. So again, one of that would mean the reaction forces at this pin, but alternatively, you have to make sure that you're drawing this force on this member, on EB, which is why EB is not a 2-force member, because it has the reactions at this pins, but also it has this additional force on it. So that's not a 2-force member. Any questions on just what I just talked about?
For the
Oh,
middle
yeah.
member, oh, no, you go.
No, you go.
Okay. For the middle member with the pulley on it,
Yeah.
is there I get the weight acting on the pulley, we put it acting on the pin of the pulley, like right there. Is there a reason that we don't put it like an inch out of because it's technically acting on the edge of the pulley, or is it? I don't. That's just something I've thought about. I don't know if that's
No, you're 100% right. So technically, it's not It's not directly acting on this pin. You're right. It's acting across the rim of this pulley, right? And the way that you translate it, because there are reactions at this pin, and it just happens to be the case that with pulleys, you end up with an equation that says the reactions in each direction are the weight of the pulley times the radius of the pulley. So in this case, it meant that the reactions are just the weight because the radius is 1. But if the radius was 2, it would be double the weight. And that kind of comes from the moment equation, because this rotation about that pin is the magnitude of the force times the distance away that the force is acting.
Okay. Got it. Thank you.
Yeah, for sure.
And yeah, I'm not sure if you're gonna go over this or not, but like you're talking about the pulley problem and the friction stuff. Will you go over how to identify which one we set as T2 and T1?
Yeah, so that's I think the next section is friction. Yeah, so
Okay.
I go over that for sure. But this is so you only have to deal with T1 and T2 if it's a string wrapped around a bar or something like that. So pulleys you generally assume are frictionless, because any friction that happens on a pulley is happening at the pin, which is a lot more complicated than what we go over in this class. If that makes sense.
Yeah, it makes sense.
All right, cool.
Hey, Allie, I just got back to my house, so is there any way you can let me in?
I thought you were in. Oh, you're not in. Welcome. Now you're in.
Thank you.
For sure. Okay, that really confused me. I'm like, how are you talking if you're not in? But anyway, so any questions on how to incorporate? So otherwise, you solve the problem entirely. the same. So like this was a frames problem, you solve it like a frames problem, you just have to consider that the pulley is there, right? So otherwise it's the exact same thing. Is there any questions on that? Cool. So the other alternative is that it's a series of pulleys, which is something you saw on your last quiz, right? So you had something very similar to this, and essentially you had a weight hanging on it, and there's a series of strings or cables coming off the top of the pulley, right? So essentially the process for this is just take this weight and divide it by the number of things coming off of that pulley, right? And then one of those will become the load on another pulley. So if this was, say, 90 pounds, right, each of these would be 30 pounds, and the 30 pounds would become the load on this pulley E here. So then that 30 pounds would again be divided by 3 to become 10 pounds, which means since this is the same cable across here, the applied force would just be that 10 pounds. Right? So essentially what that's saying is you only need 10 pounds to lift that 90 pounds, which is kind of cool. So basically what happens is it's the load divided by the number of cables coming off of the top of the pulley. And you just find out where that tension becomes the new load.
And that's only in scenarios where like the one rope like coming out from like the 3 cables on the top are like the singular like rope, because that's how you can determine they're all like the same tension, right? Like if one of the cables like the middle cable of like the bottom pulley like connected to like to the roof of the roof of the ceiling or something, then it would be like you have to solve it different.
100% right. So if you look at it, this equation, hold on, my mouse is being weird. This cable goes all the way around this pulley, all the way around that pulley, and connects here. So that is the same exact cable, which means that's how you know the tension is the same across all 3. I doubt you'll be given one where it connects to the roof. Or something that's not another pulley. That makes sense? Everyone good with that? Any questions? Maybe. Cool. Moving on to friction. I have 2 more slides for the conceptual stuff. And after we go through friction A and friction B, we'll take a break. So friction A is kind of a traditional friction problem, right? You kind of saw it a little bit in physics 1, which I think you all had to take before this class. I was told that one of the problems would definitely be the friction problem because you didn't have it on the quiz. Whoever's mic is on, can you mute it? Because.
Oh, I found him. He's in the back corner. He's hiding behind my trunk.
Hey, Jack.
Come here. Come here.
Yeah.
Hopper, come here.
I think I should. Okay, cool. All right, that was weird. Okay. So yeah, so friction, this is kind of a traditional like physics 1 friction problem. Friction is just a value that describes how much a body is resisting the motion that you want to happen, right? So there's 2 different types of motion. There's translation and rotational, which is essentially just sliding and tipping, right? Which is why you have to test both conditions. There are 2 types of friction, and we're going to talk about both of them, but the only one that's going to be on exam 2 is static friction, right? Which is the friction that resists the start of motion, right? So you know how if you're pushing a box across a carpet, you have to push harder initially to get it to move? That's because you're trying to overcome the static friction, right? But at the same time, once the box is moving across the carpet, it's not going to, like, if you push it and like stop, like if you just give it one big shove, it's going to eventually stop because of the friction between the box and the carpet. So there is a continued amount of friction once that box is moving. That's kinetic friction, but we're not going to talk about that until exam 3. So I guess conceptually, this is the friction to get the body moving. This is the friction to keep the body moving. Again, we only care about static friction right now. So here's one of the problems we were given. I like this one a lot because it kind of talks about every single thing we have to talk about. You have 2 separate bodies here, right? You have the tractor and the whatever that is. I'm assuming it's a log. So, and they're moving up a hill, blah, blah, blah. So this is one of the problems they're giving you. Because you have two separate bodies, you need two separate free body diagrams, which is kind of what I did here. So I literally just broke up the problem. So what's nice about this problem is that it again covers everything. So pretty much get familiar to breaking it up like this, because if they give you a friction problem, it'll probably cover a little bit of everything they want you to know. So here you have the reaction forces. So for every free body diagram, you're going to have a weight of the body, the force that's keeping the body from falling through the ground, the applied force that you're trying to do, and the friction that's opposing that, right? So I guess a better one to start with is this, right? So you have each component of the force, right? The important thing to know is that weight always goes straight down because gravity, but the normal force always goes perpendicular to the surface. So in this case, the normal force is going at this 10-degree angle because that's the surface angle. That being said, if it was flat, it would just go vertical. So it's always, the normal force always goes perpendicular to whatever surface it's on. And you only have one normal force and one friction because there's only one point of contact throughout this entire surface, because it is the entire surface that's in contact. Over here, when you look at the tractor, there's 2 points of contact, right? There's one at each tire, and it looks like I forgot a friction force, because at each point of contact, you're supposed to have a normal force and a friction force. So on this, I forgot to copy and paste this arrow over to here, but you're supposed to have essentially NA and FA, and then NA and FB. So that's essentially what every point of contact has: a normal force and a friction force. And then you have the normal weight pointing straight down and the pressure that's applied to the bucket. Any questions on how to set this up? No.
For the tractor, why is the friction force pointing up the hill?
I don't know. That's just the way he drew it. Maybe because the wheel is spinning this way, which means whatever is trying to counteract the spin on the ground this way would be the opposite direction. This is kind of one of those things where if it doesn't make 100% sense which arrow to pick, it'll just end up being a negative number anyway. So it's not too big a deal whether your arrow is pointing up or down the hill. Just try to conceptualize it as much as you can. But again, it doesn't really matter.
Well, he actually did say that during class. Like, the friction always counteracts the direction of the tire. So, like, yeah, if it's spinning counter or clockwise, then the friction will be going same direction the tractor is moving.
Cool. Yeah, no, that kind of makes a lot more sense. The only thing, like I said, it doesn't really 100% matter if you don't get it right away, because it'll always work itself out anyway, kind of. One thing that I don't think I put in this PowerPoint, which is kind of ridiculous that I didn't put it. Oh, I did put it up here. Okay, so that's kind of the setup for these problems. Cool.
Can you explain why each tire gets its like a separate normal force?
Yeah, so basically you have, so for this body, right, you know that the normal force is going to act right through the center of the body, or well, not necessarily. The normal force is just going to act somewhere along this entire surface, right? But the normal force on this body can only act on the point where the vehicle is touching the ground, right? So the normal force is essentially the force that keeps the body from falling through the floor, which means that it has to be at a point where the body is in contact with the floor, right? Because if I'm not touching the wall can't be pushing on me, essentially. So that's why for tires, you know that the normal force is going to be acting on the bottom of the tire, because that's the only thing that is keeping, that's the only location where you can say there's a force that's not allowing it to fall to the ground. Because it doesn't make sense for me to put a normal force right here, because even though that's the center of the body, I mean, this part right here is not coming in contact with the ground at all. There's that gap. So these two locations are the only places where there could be a normal force. because those are the only places touching the ground. Does that make sense?
For a
Yeah,
vehicle, for something like this tractor that has, normally it would have 4 wheels. Do we not have to include 4 reaction forces? We're only looking at 2, or
you're assuming that you're only looking at 2, but
right.
the reason for that is you're assuming that the back tires are experiencing the same thing. You're assuming that the slope is essentially straight in the Z direction, right? There is no change in slope.
Okay.
Which means they're experiencing the same thing. Okay. That's a good question, but only put 2, especially because it's a 2D problem. You're assuming that there is no Z component. Good questions. Anyone else? We kind of go into the calculation a bit in the next slide, so I'm not totally dodging that. Cool. Okay, so we're gonna actually look at these points down here before we go into the ones up top. I really don't know why I put these below that. But so, like I said, for each point of contact between the body that you're looking at and the ground that it's sitting on, you're gonna have a friction and normal force. And again, that's because the ground is pushing on the body you're looking at everywhere that it's touching the ground. So here it's touching the ground consistently, which means it's pushing on it entirely over this thing. So you can just say it's, instead of having an infinitesimally small like distance between each of the normal forces, you can just say there's one normal force. But here there is a distance separating the places where it's touching the ground. So that's why you have 2. Another thing to remember is that you have 3 equations, which means you have to figure out how to solve this system with the 3 equations you have. I'm going to tell you right now, if it's on an angled slope, you want to change your x and y so that that new axis is also on that slope. So essentially it's going to become one of those, like, some of the forces parallel to and perpendicular to the surface, right? Because really your weight is going to be the only thing that, your weight and maybe your pressure are going to be the things that are not perpendicular or parallel to the ground. So you want to rotate your axes right off the bat, which means it's an important thing to probably review your trig. The last thing is when you're doing a friction problem, you're solving 2 different conditions, right? So you want to see if the box will tip first or if the box will slip first, which means you're going to end up doing 2 very separate calculations. And I can't stress how important it is to understand that they are entirely separate from each other. So the first condition that I'm going to talk about is tipping, right? So if I'm pushing on a box, is the force that I'm applying going to cause the box to rotate, like flip over essentially? And the way to calculate that is by finding the position of the normal force on that box, right? So if I'm going to see if this applied pressure is causing the box to rotate, I can choose to evaluate either this corner, assuming the box is going to fall down the hill this way, or I can look at this corner, assuming that my applied force is going to cause this body to rotate about here. It doesn't matter which one you choose, because technically both are valid in this case, because, I mean, it'll work itself out anyway. But ultimately what you're going to do is take the moment about one of these bottom corners, right? And say that, well, I know that this force goes right through those points. This force I know is acting on the center of mass, or the centroid, right? And then my normal force, I know the magnitude from my sum of the forces equations. I just need to find the perpendicular distance, right? So that's your unknown in that equation. You know, the sum of the forces is going to be equal to, or the sum of the moments is going to be equal to 0. And then you're going to solve for your perpendicular distance. If that perpendicular distance is within the base of your object, right, within whatever is keeping it from falling through the ground, that is going to assume, that's going to say that it doesn't tip, because that's saying that it's rotating about this point, which can't happen because there's something supporting it on either side of that point, right? But if you get it that your perpendicular distance is like somewhere over here, this body could absolutely rotate about that point because there's nothing counteracting that rotation on either side of that point. You know what I mean? Does that kind of make sense conceptually?
Yeah.
Cool. Oh my. So that's one thing. So that's tipping. You do a moment equation to solve for the perpendicular distance of the normal force. The slipping condition is maybe a bit more complicated, maybe not. It depends on how you look at it. So you calculate the friction force on your body, right? From sum of the moments in the parallel direction equation, solve for the actual value, right? Then you separately solve for the maximum friction value, right? Which essentially is the mu sub s of the relationship between the two, or the body and the ground, right? And then you go and solve. So you have the normal force from the some of the perpendicular forces, you have the friction force. Okay, so and then you're given the mu sub s, right? Then you find the max friction, which is just mu sub s times the normal force. And then from there, you compare your friction value to the maximum friction value. If your friction value is less than the maximum friction, then it is not slipping, which means you're not overcoming that friction that's holding it back. If your calculated friction is larger than that, you have already overcome it, which means it is slipping. Does that make sense to everyone?
Mm-hmm.
And the important thing is that you treat each test separately. So whatever perpendicular distance you find in this equation, you don't use in this analysis, right? So each one has to be 100% separate from each other because you're testing two very separate conditions. And that becomes super important if the question is saying something like, find whether the box is slipping or tipping first, right? Because then you're not generally, so then you're ultimately solving for the applied force, right? Kind of like we did, there was an example problem where we did that. You're essentially just finding which applied force is required for each condition to occur, and then whichever one is smaller is the one that happens. So then it becomes super, super important to treat each test entirely separately. Any questions on that part before we go into belt friction? Silence is a no. All right, cool. So moving on. Belt friction is kind of something that they threw in right at the end. So this is something that I would kind of assume you don't have a lot of practice with. If you do, good on you. So essentially belt friction is when you have some kind of rope wrapped around a bar, something's hanging down from one side and you're pulling on the other side, right? In statics, that box is not moving. The box or whatever you're hanging on one side is not moving. You're not pulling it up, you're not lowering it down. The question is going to ask for a range of forces to keep the box staying still, right? Which means you're going to have a maximum forces, or a maximum applied force and a minimum applied force. So in that sense, you're going to need to assume two different occasions, right? So to find the minimum applied force, right, you're assuming that the box is barely being kept up. You're barely being able to hold the box up, which means the box is essentially about to fall down. So the motion, or the direction of the motion, is the box moving down, which means your hand is moving up, right? Because it's all one cable, so if one side falls, the other side rises. So in that case, T2 is the direction of motion, which is the box going down, your hand going up. T1 is whatever's counteracting that, whatever is trying to oppose that, which means T1 would be the force that you're applying to prevent that from happening. Does that make sense? Okay, similarly, hold on, I gotta chat. Okay, cool, that makes sense. Similarly, if you are trying to find the maximum force applied, you're saying, I'm about to yank it hard enough for the box to start going up. So I'm pulling harder than the box needs me to pull, right? Which means your hand is going to go down, the box is going to go up. So which force would be the force counteracting that movement?
Oh, you said T1 would be counteracting the motion.
Yes. So what quantity would be counteracting that motion?
The weight of the box.
Exactly. So because the box, in the case of finding the maximum force you can apply, your hand goes down, the box goes up, right? Which means the thing pulling the box down is the weight of that box. So in that case, T1 would be the weight of the box, T2 would be your applied force. Everyone cool with that?
Mm-hmm.
Okay, these two values up here, mu is the coefficient of friction between the rope and the bar. That's usually given. And then beta is the contact angle, or the angle describing how much of the rope is in contact with that bar in radians. The important thing is to remember the radians. So if you're not very familiar with the unit circle in terms of radians, I would look at that. They're always going to give you some kind of angle that's defined. So it would be like a 30, 60, or 45 kind of angle. Or I'm sorry, 90 or 180. But you'll get some kind of angle you're familiar with. They're not going to give you like a 2 pi over 7 kind of angle. So beta will always be something that's easy enough to find that you should be able to do it from there. Any questions on this equation? None at all. Okay. All right, so again, before we go into this, we'll take like a 10-minute break. I'm sure you guys are kind of exhausted by that. We've been almost an hour and a half now. So, yeah, so just take a 10-minute break. We'll come back at 1:30. And then, yeah.
Oh, I'm sorry, Allie. On the last slide,
Yes.
for the belt friction, I
Yes.
know you were saying you made T1 the weight of the box since it was opposing it, but when you're finding the range of tensions needed to keep it in place, wouldn't you, once you do it that way and calculate it, wouldn't you switch T1 and T2 and then do it that way to get the other like end of the range?
Yes, exactly. So for the largest one, you're pulling, so the largest applied force to keep it in place, you're assuming that you're pulling it down hard enough for the box to start going up. So since the box is going up, the thing pulling the box down is its own weight. So in that case, you're right, T2 is my applied force because that's what's making the box go up, but T1 is the weight of the box because that's trying to keep that from happening. In the other case, you're trying to find the smallest applied force to keep it there, which means your hand is about to almost let the ball or the box fall, which means the direction of motion is the box going down and your hand going up. So the thing opposing that motion is the force that you're applying. So T2 would be the weight of the box. T1 would be your applied force.
And how do you switch that with the equation? Do you just put like T1 equals T2 e to the UB, or?
So not necessarily. I guess technically you could, but you would just plug in. So for one case, you would say F equals W e to the whatever. And then for the other case, you would say W equals F e to the whatever. Because F is your applied force, W is the weight of the box.
And I know you said you don't have any like last review you kind of went over some problems. You said this review you don't have any problems we're going over.
Maybe depending on what time we finish. I do kind of have a meeting at like 2:45, so if we finish early and have time for problems, absolutely. I have a lot more content in terms of preparing you for actually doing the exam, assuming that you can do problems on your own. If not, I have office hours for I think 3 hours before now in the exam. I have Monday afternoon and Tuesday morning, so I guess only 2. So I have 2 office hours that you can go to for more practice if you need it. But if we have time, I'll go over problems today. If not, it'll just be a matter of going to office hours, I think.
Okay, thank you.
Of course. All right, so 10 minutes, we'll just do 1:35. I will be back. Okay, so jumping back in. This kind of covers the part that you guys were talking about. You're not really comfortable with distinguishing what to do when you're first looking at a problem, which is fairly common because a lot of the times they are either asking for the same thing on a different like structure, or they're asking for I guess that's the only thing that could happen. But the questions might sound very similar. It's just a matter of how to solve it. So some quick suggestions before we go into kind of like an activity is you should probably pick apart the problem given before you jump into any kind of calculations. So my recommendation is establish what structure it is right off the bat. So there's only really a handful of structures that could be in the problem. So truss, frames, cables, pulleys, or is it a friction problem, right? So right off the bat, some of these have like methods associated with them. Some of them have like pretty fundamental steps that you do. So by picking out what structure it is, you can kind of narrow down what options you have in terms of how to move forward in the problem. Once you identify all that stuff, look at what the action item is. So basically, what is the question asking you to do? And once you identify that, you can figure out which steps from the list that your structure narrowed down you would actually want to move forward with. So once you kind of pick it apart, draw the free body diagrams. Like, even though they give you a question, you're going to have to draw one anyway. I'm pretty sure on the second exam, they don't give you, if I'm right, if I remember correctly, they gave you what free body diagram they wanted you to draw the last time. I don't think they do that this time. I think you have to actually draw it on your own without them asking you to. Could be wrong, but draw it anyway, regardless of whether you're asked to do it or not, because it is points. So draw the free body diagram, and then from there, look at what unknowns you have and how many equations you can use based on like the structure of it, the unknowns that it ended up working out to having. Again, with frames, this might not necessarily hold 100% true, but like what kind of assumptions can you make? What simplifications can you make? Like, are there 0 force members, 2 force members? Like, are you assuming something that simplifies the problem? Stuff like that. So kind of simplify it before you even jump into the math if you can. So this is kind of how the next, like, I think 4 or 5 examples are going to be. I have a sample problem. This is one of, I think all of them are samples from the list of review problems. And I kind of just want to walk through the, like the approach to it, like how to, before you start doing the calculations. So I guess I'm going to start asking the questions, and people who want to answer. And if no one's answering, I'll call people out. But what type of structure is this?
Truss.
Exactly. So either you can recognize it from the structure, or it literally says it in the problem this time. So what methods or steps are commonly associated with trusses? I'll give you a hint. Trusses are 2 methods.
It's just a method of joints or sections.
Exactly. So what is this question asking you for?
Internal forces in
It's
like
AB, AF.
5 members.
Yeah, exactly. So it's determine the internal forces in whatever members they're asking for, right? So that is your action item. That's what your answer is essentially going to be. So looking at what those members are. So you have AB, AF, FE, FC, and BC. Is there a way for you to cut through all of those members and expose all of the internal forces?
No.
No.
Yep.
Well,
Oh, no.
no, there's not. And the nice thing is that since they're all kind of like connected to each other for the most part, you can go joint to joint. So for that reason, what method up here would you use?
Joints.
Exactly. So what would your first step be?
External forces.
Yeah, you want to find the forces at A?
And at D, right?
Oh, yeah, and D.
A is probably the one you're going to use, but if you wanted to look at it from this side and go that way for whatever reason, or if they ask you for, instead of AF and AB, if they ask you for CD and ED, you would want to find them at D too. So yes, you're 100% right. Solve for external forces. And then what? So now you know the reactions at A. Then what?
And you
Go
cut
from
it
there.
through like
Yeah.
F or AF and AB and then do method of joints.
Mm-hmm. So you're right. Isolate one joint and use the method of sections, and you're right. You start with A, and then where do you go?
Probably B.
Or F.
I would go to F because you already know. So the ones that they're asking you for are AF, AB. So you want to find FE and FC too. So I would go to F because
Okay.
then you can find out those are, and then, or well, fuck, I guess B and then F. It doesn't matter. So these ones, if you can do them, they can go in either order. I think the solution did B first, so that's why I put B first, but you could do it in either order, I believe. But yeah, so any questions about this one and how this like mindset kind of helps at all?
Could you first do like a method of joints at A and then do a method of sections like cutting through FE, FC, and FB, or is that too much work?
That's a lot of work. I don't really know how that would benefit you because you would still have to find, I mean, you could. I don't see why you couldn't, but it's a lot.
I think that's sort of what me and my group did on the project, I think. I don't know if that applies to this example as well, or if that was just for that project, but
You absolutely can. So there's no reason why you couldn't find these by the joint and then cut through here and then expose those three and then either look at it from the left or right side. I just don't know if that simplifies it or makes it more complicated. But if that's what you wanted to do, there's nothing wrong with that.
okay.
Anyone else?
I don't think it has something to do with this, like what it's asking for, but I was wondering, at point D, is that a roller?
Yes.
Okay.
Which the truss can slide left and right, and it could rotate, but it can't move up and down. So your only reaction would be a vertical reaction.
Okay.
Good question. Anyone else? If not, I'm going to move to next problem. All right, cool. What structure is this?
Frame.
The frame.
Exactly. How'd you know?
It's not a truss.
That's frame with the problem.
Oh, yeah, that too.
Both are correct answers. Very nice. What steps or methods are usually associated with frames? These are definitely steps, not necessarily methods.
I mean, you pull the pins.
Exactly. That's like the unique step is you pull the pins and look at everything separately. So what's the action item? Like, what's it asking you for?
The component forces it A, B, and C.
Exactly. And the important thing to remember is it's asking you for them on ABC. So you can't like pull it and then write your answer as like CX and CY equals blah, blah, blah on CD, because technically you're not answering the question. It wants it on ABC. That's an important thing, because it's asking it on member ABC. So, I mean, it doesn't really apply because you're going to do those steps anyway, so you don't really have a choice. So what would your first step be?
I don't know about first step, but just a question. Are BD and BE two force members? Like, because there isn't any forces acting, like, on the joints of them. But I know it's, like, on, like, DE, there's, like, those two, like, 300 Newton forces acting on it.
So I think BD is for sure. BE, yeah, BE.
Oh, I guess E. Well, yeah.
Yeah, so I think they both are.
Okay.
So
Okay.
that would technically be your first step. And then what would your next step be?
Put all the reactions of the pins.
Exactly. So you pull all the pins out and draw free body diagrams. And then what?
I mean, you just got to go through, like, where you can and solve for variables and then find
Like,
them all, I guess.
yeah.
Exactly. So you just solve for your unknowns. Very good.
Oh, this is the same one that's on the review.
Yeah, all of these questions are from the review. All right, what type of structure?
The frame.
What method or steps does this have? And it's the same as the last one.
Yep. Just pulling the pins, yeah, and cutting the member.
Yep. So you do pull the pins for frames. This one, since it's an internal forces question, that's, I guess, the method I was talking about when I wrote this. But yeah, so it's asking you for the internal forces. So you cut the member and expose those. So what's the action item?
The internal forces at E and F.
At E and F.
Exactly. So again, there's not really a choice of what methods you use. But what's your first step?
You want to separate it so you work only on the BC section because it has the least amount of unknowns.
Well,
And then
there's a step before that.
Oh, it's pulling the pins, I guess.
One before that too.
Finding the external or
forces.
the reaction forces.
Exactly. So because when you cut something, you expose every all three unknowns at that cut, you have to have, like, so at point F, I would look at it from this side because you'll have one force up, one force down in a moment, and then here you'll have one force down, one force up in a moment. So like that would be the simplest way to do it, and then here this would be the simplest way to do it. So really you're only using all this nonsense in the middle to find the reaction forces, which is kind of
the weird thing about this question is that I did it that way when I solved this one, is that I found the reactions at A and D to find the internal forces, but in the answer sheet, they just completely ignored them entirely, and they just used the forces at B and C in order to find the internal forces of E and F. You get the same answer either way, but it's just another way of doing it.
right. You can do that too, because if you separate all of these, you know that the pin reactions at B and C, if essentially if you cut it here, you're only looking at EB at that side of the. But I mean, personally, I think it'd be easier to just look at this instead of trying to deal with all that in such a complicated way, if that makes sense. You're right, though. You could.
Both work. I tried it both ways to see if it worked.
Yeah, no, they absolutely do both work, but I'm just saying, personally, that would be easier, so that's why I put it. All right, what would the next step be? So you found your external forces or your forces at BC, and I mean B and C. What would you do?
Cut the member at E and F.
Exactly. So if you cut the member at E, use your equilibrium equations on either AE or EB. And if you cut the member at F, you use your equilibrium equations on either CF or FD, right? So it just depends on which cut you're looking at. All right, cranking along. what type of structure is this? Or I guess what type of problem is this?
Friction.
Friction. What gave it away? Was it friction 2? Probably. What methods and steps does this structure have? Or this problem, I guess, have?
You gotta draw your draw the forces on the system to like identify where like the friction forces and the normal forces are.
Right. So really the big thing about friction problems is that you're really heavily relying on your free body diagram. And does anyone remember what the two newish components are for the free body diagrams?
Friction and normal.
Beautiful. Excellent. So what's the action item?
Forces to produce an impending motion. So like, because you need to find like the force you need to push on it to make the box
So just
slide.
finding like the slipping and the tipping, I guess.
Mm-hmm. And then also you find the height. But yeah, that's the main piece. And then which method would you use to solve this problem? I'm pretty sure that's NA2. Yeah. So then what's the first step?
I mean, drawing the free body diagram, I guess.
Yep. That's what I think. Yep. So, boom. And then what would the next step be?
I guess just deciding whether or not you want to do slipping or tipping first. I mean, you can do either or. No.
But no, you're 100% right. Needed to impede the motion in either case, right? And then for slipping, you would compare the friction value that you find for that value of P to the maximum friction. So I guess technically in this case, you would solve for the maximum friction, and then what you would do is compare or find F max, and then assume that the F in your free body diagram is F max, because that is assuming that the force would cause the slipping. And then from there, solve for P, like that's part of your, assuming that F max is the friction on your free body diagram. And then for tipping, you would basically find the position of the normal force on or around the body as normal. But slipping is the one that's kind of weird in this case.
For the second part of the problem, is it just asking to find like the height that would make the the force needed to tip it equal the force needed to make it slip?
Yes. So basically you would set P equal to each other, and then you would assume that F max is the friction, right? Because that satisfies the slipping condition. And then you assume that the normal force is acting right on this bottom corner. Where the hell is my mouse? Hello. Right on this bottom corner. Because if you're pulling this way and the normal force is here, that's why it's going to tip. And then from there, you just you take the moment about one of the corners and solve for H. So you take the moment about here, and then it would be P times this is the perpendicular distance, and you're solving for that.
Okay.
Cool. Anyone else? No. All right, the two people that have been talking this whole time do not get to talk. So, all you quiet folks better chime in. What type of structure is this?
Cables.
Cable, beautiful. And then what methods or steps does that structure have?
Method of sections.
And
joints.
And joints, beautiful. Because it's both. You have option to do both. And then what is it asking you for?
The sag at point B.
And
Max tension.
Q. All right, and then how would you do that? What method would you use?
Method of joints.
Exactly. Because it's asking you for most of them anyway. So there would be you're doing two steps anyway, right? So if you're trying to find the maximum tension, it has to be in one of these two side components, right? Because the maximum tension is always at one of the joints that connects to the wall or the support or whatever it is. You just needed to confirm that it was, because you don't know YB, so you have to confirm which one has the higher slope. So either you have to find the tension in this cable AB and in CD anyway. So either you would be cutting it and just kind of doing some kind of weird version of method of sections, or you would do method of joints at A and then method of joints at D to find that. And then you just do trig to find Y. Oh, wow, I just gave away all. Okay, well, the first step is what? One of you quiet people.
Free body diagrams and then taking method of joints at whichever one you want to do.
So yes, but what do you have to do before you separate it into a method of joints problem?
Call for external forces.
Exactly. Which are the reaction forces in this problem. All right, so reading the problem, someone tell me what's kind of weird about this one. Or like what's one thing that a lot of people are going to forget. Hint, I've brought it up already today.
Is it remembering to convert the kilograms into newtons?
Exactly. So because kilograms is a value of mass and you're using, because all free body diagrams are description of all the forces acting on your body. So you can't put a mass on a free body diagram because a mass is not a force. So you would convert this mass to a weight by multiplying it by gravity. So that's the big thing you have to do here. So because it's kilograms and not newtons, you would have to multiply by 9.81. All right, so now that that's covered, what are your next steps? So you've already found your external forces. What do you do next?
Find the tensions at AB or DC.
Exactly. And then what?
I mean, couldn't you only do DC because you don't know what YB is, or?
No, so you can do, so here you could do some of the forces, right? Because you know that this is just a component of that. So you know that the X component here would equal the X component at your reaction, and the Y component would equal the Y component at your reaction.
Okay.
So that helps you find what? So now that you know the components of this, what can you find?
You can then find the YB by using those components as like a rise over run equation.
Exactly. So basically, you know that the slope of whatever this is, right, whatever your reaction force resultant is, it has to be the same slope as this cable. Kind of going back to what I said earlier in like the cable slide, that your reaction force has to be parallel to the cable anyway, because it's just opposing the pull on the wall. So you know that the slopes are the same. You know that the slope would be rise over run. So in this case, the rise is YB, the run is 1. So YB over 1 equals whatever that slope is. So YB equals that slope, which is pretty cool. This one simplifies nicely. But if that wasn't 1, you could still do it. Any questions? Cool. So those were that's kind of the logic that I would walk through every single time, right? So figure out what the problem is solving, come up with some kind of approximate plan, at least in terms of the first couple steps, and then like do all that before you even start solving the problem mathematically, right? Because that kind of, we'll go over that a little bit here. So this is kind of the ideal solution, right? So like what steps can I do to A, make sure I don't like put myself into a corner where I keep making a bunch of mistakes, and B, how do I do the problem so I get the most partial credit? So setting yourself for success, basically there are absolutely ways that you can work through the problem so that you're getting so you're not screwing yourself over in terms of making a mess and then losing track, right? So step one, please read the question, because a lot of people, especially with now that like all the frames problems could either be asking you for pin reactions or internal forces, and that would totally change the approach of the problem, because problems can look the same and ask for something entirely different. You should absolutely read the problem before you even draw anything. So that's something that I saw a lot on the last exam, is that people would start solving the problem, realize that they're on track to solve something completely not what the question's asking, and then you screw yourself over with time, and then you have to completely start over. So that's the first thing. Please, dear God, read the question. The second one is, you guys saw how much paper we had to give you last time, right? So if you have to draw a free body diagram that takes up a whole page of free body diagrams, do it, because that's going to be what you use to solve the rest of the problem, right? So once you draw your free body diagram, you shouldn't need to look at the original drawing. That's how you know it's right. That's how you know it's a good free body diagram. So if that's going to be what you're using to solve the problem moving forward, make sure it's good. Make sure you can read it, make sure it's accurate, and do all of that before you even do the math. So that's another thing. There were a lot of really, really tiny free body diagrams last time. So take up the rest of the page and then start doing math on the next page. It doesn't matter. If it's going to help you get it right, it's going to help you get it right. So the next thing is establish right away what your unknowns are and how those do or don't relate to what the question's asking for. Because the question might be asking you for the pin reactions in a frame, the pin reactions at pin B, but you have 5 pins and like a couple 2 fourth members, so you got like 1,000 unknowns. So figure out how you can relate those to each other, and then from there figure out what kinds of equations you have. So there's only 2 options. You either have a non-concurrent force system with 3 equations or a concurrent force system with 2 equations. So from there is a way to solve for the unknowns. So they're not going to give you a problem that won't work. So if you have too many unknowns for your equation, either it's a frames problem when you're supposed to, or you forgot to simplify something, or you're kind of using like the wrong approach in terms of concurrent versus non-concurrent. But know that if you sit there and blank, there is a way to solve the problem. They're not going to give you a problem that won't work. So, I mean, my last tip is to logic check your answers, right? So does your number make sense? Did your units match up? Are they the correct units for the quantity you're looking for? Like if you find an answer in Newton meters, but it's a force, you missed something. Check your sig figs, check your directions, and then, so these are all steps just to make sure that you're not making the problem harder for yourself than it should be, right? But that being said, it's 100% possible that you just don't necessarily know how to solve the problem, right? And that means that you're either going to get 0 out of 100 points for that problem, or you're going to finesse it a little bit and find a way to kind of use the system to get at least as many points as you possibly can, right? So the important thing that it took me a long time to realize this myself, actually, is that this is an engineering mechanics exam, right? They're testing your knowledge on engineering mechanics, not how well you can plug stuff into a calculator, not really how much you know your trig, so stuff like that. So they're asking you for information about the structure, how you would approach it, how you choose to draw your free body diagrams, your understanding of the angles, and the equations that you choose to use, right? So if you get a number wrong and plug it into the equation and get the wrong answer because you use the wrong number, as long as that's not from a fundamental like mistake in the mechanics, you should be fine. Like that'll be minimal points off. But there's a way to kind of finesse that if you get stuck. or if you're running late in terms of the time you have left, or if you just totally don't know how to come back and like how to start the problem, right? So I kind of talked about this a little bit last time, but I really wanted to lay it out because I didn't see a lot of you guys taking advantage of the partial credit. Because if you don't know how to do the problem, there's still a very like simple way to get half-ish of the credit, right? So if you get stuck, right, on one piece of the problem, like I don't know whether to use sine or cosine, I don't know this number, or this number doesn't look right, and so I'm going to plug in a number that would look right. Just literally write in the margin, I forgot how to do this step. I'm continuing the problem with whatever value you were looking for equals, my number was 7. Dr. O'Neill called me out every single time because I would just plug in a 7 if I forgot a number, or if I didn't know how to find a certain number. So, like, they use error carried forward so genuinely or generously in their grading, which means that if you make a mistake, they're only going to take off for it once. So if you do the rest of the problem correctly with that mistake that you used or that you made, you get the rest of the points. So you obviously won't get the full credit, but you're only going to miss the points that went into solving for that one number that you couldn't remember, as opposed to, oh, I blanked and then I can't finish the problem, so I'm not going to finish the problem. You know what I mean? The next thing is what happens if you run out of time, right? So if I spent way too long on question 1 and now I can't finish question 3 and finish question 4 at the same, like one of them is going to be left completely blank, blah, blah, blah. What can you do, right? So you're not going to get full credit, obviously, because you didn't finish the problem. But by writing out your steps and showing that you know some of them, like enough of the mechanics, you're going to get some points. So that's especially important with like, remember the frames 2 problems that had like 6 or 7 steps in them that you kind of hop from one free body diagram to another, like stuff like that. If you write out the steps that you plan to do, it's going to give you a like guideline for how to do it moving forward without forgetting it or forgetting where you're going, but it's also going to show that you knew what you were doing. So if you made a mistake in one of those steps and that ended up propagating towards the end of the problem, like that's the steps that you write out at the beginning is going to end up covering you by saying, hey, I knew what I was doing, I just made a mistake somewhere. You know what I mean? But at the same time, that can also say, hey, I knew what I was doing, I just spent way too long on question 1, blah, blah, blah. So that's another tip, is just start writing a general plan. Obviously, don't write out a plan long enough to like end up screwing you over in terms of the time that you have left anyway. So if you're not going to have enough time to write out a plan and solve the problem, but you think you might have enough time to write or to solve most of the problem and write out a plan, then write a kind of very general plan. But I can't even express to you how important this step is. Like if you think you're screwed on a problem, just start writing out the steps you would do. So I guess the last thing to cover is like what happens if you look at a problem and say, I don't even know what the heck to do. I don't even know where to start. I would literally just run through the questions from back here. What kind of structure is it? What steps does that structure have? What is it asking me? How can I get from the steps that I have available to me to a final answer? Blah, blah, blah. I would go through that kind of stuff. Always start with a free body diagram because maybe you're just not seeing something 100% of the way. Blah, blah, blah. And the last thing is, I can't even stress enough how important it is to logic check your answer. Because if you get a question and all of the forces in your problem are like 1 Newton or 6 Newtons or 7 Newtons, and then you get a normal force that's like 750 Newtons, right? That should be a red flag, right? You should be able to say, well, how in the heck did I get like newtons that are in like the 10s and 20s kind of values to equal a force of 750 newtons. So if you get there and you can't figure out why the answer is wrong, but you know that the answer is wrong, write it. Say, this is the answer I got. This isn't correct. This is way too high, blah, blah, blah. Explain why it doesn't look right. You'll get credit for it because you know enough about the mechanics to say, you won't get full credit, but you'll get more credit than you would by just saying, oh shit, it's wrong. Like, nothing I can do. You know what I mean? So you'll get more credit than 0, I guess. So you're showing that you know enough of the mechanics to know that value is wrong, but you don't know exactly how to go make it right. So there's that. So this is another important part. This, I think, corresponds to like the last section in the guided notes for whoever's using it. What should all your answers look like, right? So some basic information. Significant figures. For numbers that start with 1, you use 4 significant figures, and for numbers that don't start with 1, you use 3. This rule should only be used in your final answer. So use more than 3 and 4 sig figs in your calculations, because by using only 3 or 4, you're creating an error in that value that you're rounding, and then that error gets compounded as you continue to use that number. So only round when you're in your last like answer step. So for units, you only have a few options, right? So for forces, you either have newtons, pounds, or kips, and probably only newtons or pounds. For moments, you have newton meters or foot pounds, right? So moments are force times distance, which means you're going to have the force unit times the distance unit. And then for distance, you're going to have meters or feet, right? That doesn't mean that they'll only give you these units. You might have to convert them, but those are what your answer options are. So the direction is going to come from some kind of conceptual knowledge of the body, right? So I'll talk about that more in a little bit, but it'll have something to do with the assumed direction that you chose and whether the math showed that was a correct assumption or not. And finally, which body, you only write what body it's acting on if it's required that you do that, right? So does that force show up on more than one free body diagram? If it does, then you have to indicate which body it's on. But just like they'll take off points if you don't tell what free body diagram it's on, if you tell what body it's on and you don't need to, then they're going to take off points for that too, because then they don't know that you actually know why you're writing it. They just think you're writing it for shits. So that's that. Any questions on like what your answer should look like from here? Like the basic stuff.
I have a quick question on the previous slide.
Yeah.
Like, why are they so generous on like the application of like the numbers and stuff like that?
What do you mean?
Like, why are they so generous on the partial credit? Like, in case like you do like get the number, because like most of the on my first exam, I mostly got points and passed because of the partial credit. Like, why? Because I know some of my other classes aren't as generous.
Because I mean, especially if you're looking at like a math class, they're testing you on how well you can do the math. If you're looking at a mechanics class, they're testing you on how well you understand
the process,
what's going on in the statics, right? Like, why do the equations look like they do, not how did you plug things into the equation.
Okay, I got you.
It depends on how, like, what your mistake is with the math. Like, if you plug in centimeters instead of meters, that's kind of a fundamental misunderstanding of the mechanics, because you'll get a number that's 100 times too small.
Okay, yeah.
So it depends on what your math error is, but for the most part, they really only care about the mechanics knowledge, which is why your priority should be to show that you know the mechanics.
Okay, thank you.
Yeah, for sure. It's a good question. So if you ever get stuck, or if you're blanking, or if you're running out of time, just do whatever you can to show the most knowledge of mechanics. That's the bottom line, because that's really what they want you to know. All right, so kind of going into it a little bit, specifically for each answer. So if it's a truss problem, you need magnitudes, units, and direction, right? And then the weird thing about truss problems is that it's either going to be in tension or compression, because each member can only be pushed on or pulled on, because really they're all two force members, because every applied force will be at the joint. So it'll either be in tension or compression. For frames, because you're pulling all those pins, you need magnitude, units, direction, and which body it's on, because it'll be acting on one of the free body diagrams as you chose to calculate it. You know what I mean? So if it's up on AB, it might be down on BC. You know what I mean? So it's important to look at which one, or to specify which body you were looking at, because that'll help them verify that your direction was right. For internal forces, you're going to need magnitude, units, direction, and body, because when you cut, you expose equal and opposite forces. So depending on which segment you choose to look at, you're going to have a different direction, because they should be opposite. For cables, again, you only need magnitude, unit, and direction. But in terms of the direction, I think that because all tension, or all cables are in tension, you might not need it 100%. And it kind of varies in terms of like the solution guide. So I couldn't actually find a 100% confident answer. So I would say like 700, like tension in AB is 750 newtons in tension along cable AB. You know what I mean? Like, so specify it, but they're not going to take off points because it's redundant, because it's not necessarily redundant. Like, you don't know for a fact. Like, there is no case where you would have to specify it for cables. So there's that. Pulleys, magnitude, units, direction. Pretty standard. Friction, magnitudes, units, direction. The important thing is on these ones that have direction, if it's on a slope, specify the slope. So don't say like 20 newtons and then draw an arrow in the direction of the slope and just hope he knows what you're talking about. Draw it and then measure the angle that they give you, like label the angle on that arrow you drew. That's an important thing, because then they don't actually know if you know what direction it's going in. So that's kind of the end of what I had prepared. Just type your name in the chat again so I can make sure I know who stayed the whole time and who left early. I know a couple people told me they had to leave early, but make sure that you're letting me know. And then do the post test, please, because I use this for my class that I'm in. And then I believe we might have time for a question. I don't actually know what time it is. Anyone know what time it is?
It's 2:18.
Okay, so we might have time for one question. Unless you guys have a couple conceptual questions you wanted to go over. Anyone have anything conceptually? No. Not at all. How are you guys feeling kind of about the exam? Worried? Ready? Still gotta study?
Better.
I'm not worried. I just need to finish up the 9 questions you guys posted.
True.
I should be fine after that.
I thought there were 18 or 12 questions.
Oh, is there? I don't remember.
I don't know. I think there was more than last time.
Oof.
But yeah, I can't stress enough how important it is to do those problems. And there are a lot of people. Colin, did you come in late? Did you leave? You might have left.
Yeah.
Oh,
I
okay.
thought it started at 12:30.
Oh no, you're good. I just wasn't sure because I didn't have you written down at noon. I gotcha. Boom. Yeah.
You said 4 questions, or how many?
It's 4 questions on the exam, and I would assume that either all of them are going to be on the shorter side, or one of them is going to be really, really quick.
Okay. Okay.
Any other questions?
I was wondering, like, if you could do a question with the friction, but using like the T2 equals T1 times, or what, like that equation with the tensions.
Yes. Give me. One second. So, did you have a problem in mind, or did you want me to just pick one from the lessons?
Like, you could just pick one. I'm like a little confused on like how to use it. We don't have to like do the whole problem like all out, but just like knowing like what to do using that equation.
Oh, okay, yeah, for sure. So here, let me pull up one of the worksheets. Friction 2. Was that 2 or 3? Does anyone remember? That might have been friction 3. Okay, let's do this. All right. Share my screen. Can you guys see this problem?
Oh yeah, we started working on that one in class.
Yeah, so I chose this one because you haven't finished it yet. Or well, you might have, but you did it on your own. So the important thing to remember is that, hold on, who messaged it? Okay, cool. So the important thing to remember is that there's 2 things that you have to establish pretty much right off the bat that determines the correctness of the problem, right? So you're in charge of determining where the motion is and what that means for the, like, which T is which, right? You're also in charge of deciding what beta is based on the drawing, right? And in this problem, the beta part is a little bit more complicated. So let's start with the T thing, like which tension is the one that we are calling T1. Let me take a screenshot of this, and then I will open a Word document. Boom. All right, so here's this. So basically, first of all, I apologize in advance if my handwriting is terrible. My computer doesn't like using this little writing pad thing when there's a Zoom call open, so it might be a little bit glitchy, but we'll work with it. So in terms of which T is which, right? Can you guys see the screen still?
Yep.
Okay, so it's asking you for the range of values again, which means you're going to have some minimum applied force and some maximum applied force, right?
Would it be wrong if, like, because since you know, like, you say you use the same equation both times, except like you just change whether it's T1 or T2 where you put like the weight of the weight pulling it down. Would it be wrong if you just plugged in like to both and then solved and like, oh, that's my range? You're like just like analyze that without like, I mean,
if you do the calculations right, the range will be correct, but they want to see why T1 and T2 would be, like why you chose that, because it's so easy to just plug in those numbers, flip them and say, hey, I know the mechanics, but they want to see that you know the mechanics.
Okay, got it.
So you'll get the range correct. You just need to make sure you're justifying why T1 is what it is. So, okay, so here we go. The range of values to make sure the cylinder will not move up or down, right? Given that this is 45 degrees, right? So here we go. So if for my minimum value of P, right, this P is barely enough to hold that box up. So if this isn't strong enough, this will start sliding that way, right? It'll be the force that this block is pulling on P will not be larger than P. So this will start to pull this way. Since this block is connected, that'll start moving down. So that's your motion, right? So that's T2. So T2, here, let me erase this and I'll just do minimum in purple and then blue in. Okay, so your motion is T2, and what quantity describes, or what quantity would cause this block to fall down? Your options are the weight here or the P here. Anyone? So which would be T2 if you know that the motion is moving down?
T2 would be
Would
the
it be
weight.
P or it would be the weight?
So it would be the weight, right? Because if this block is moving down, the motion, the weight is what is pulling it down, right? T1, or what's opposing that motion. So this force is the thing that's not causing it to just straight up fall, right? So it's not 100% falling like freely because you're resisting it up here. But so your P is opposing the desire for this block to fall down. Does that kind of clear it up a little?
Yeah.
All right, so if you're looking at your maximum P, which means you're pulling on this so hard that this force is stronger than the weight, or it's about to be stronger than the weight, that means that the motion would be going up here, right? Because if you're pulling stronger than this is pulling down, this is going to go up. And that also means that this is going to go to the right. Because if this goes up, since it's all in one cable, it has to move together. Right? Does that make sense?
Yeah.
Okay, so if that's the motion, we know that, so basically, how about we do it this way? So we know that P is one of our forces and P is moving in that direction, right? We also know that weight is one of our forces and it's moving in that direction. So which one of these two red forces is moving in the direction of our motion for the maximum P?
The weight?
The weight is moving down, the motion is moving up.
Oh, then P.
Yeah, so the motion is moving right up here and P is moving to the right. So that's in the same direction, so T2 equals P. Which one is moving in the opposite direction?
The weight.
Exactly. So that's why these two are what they are. Does that kind of clear that up a little bit?
Yeah, okay, so the minimum and max, that's basically like what you wrote in purple and what you wrote in green. Are those like the, why did you exactly switch them? Because I'm a little confused, like with the two different motions.
Yeah, so basically, because it's asking you for a range of values, you're going to have two different motions associated with it, right? So you're going to have, it's asking you for the values of P that the cylinder doesn't move, right? Which means that to find the actual range of values of P to make sure it doesn't move, you have to almost assume that it's about to move, right? And you have two options. Either the block can move up or the block can move down. And if the block moves down, it means you're not pulling hard enough to keep it up. If the block moves up, you're pulling too hard and now it's going, now you're pulling it up essentially. So that's why you have two different motions, because you're trying to test the extremes of essentially non-motion, right? So right now it's at a balance. You want to throw it out of balance in each direction. And because for the minimum value, you're saying you're not pulling hard enough, the motion for the purple would be going this way. And the motion for the purple would be going this way, which means, let me erase this because that's kind of confusing. Which one is going in the direction of the motion? So you have weight going down, or the movement going down and the weight going down, or you have the movement going to the left and the P going to the right. So which one is going in the direction of the force that we're looking at?
The weight?
Exactly, because these arrows are pointed in the same direction.
Okay.
So that would be T2, because they're pointing in the same direction. Here, these two are pointing in the opposite direction. So that's T1. And that's just for this equation, because this equation, the minimum value determines the motion. The maximum value determines that the motion is up and to the right, which means that the motion up is now counteracting the motion of the force, which means that is the opposite now. So since these arrows are switched, it's now in opposite directions, which means this is counteracting that. And T2 is now in the same the applied force is now in the same direction of the motion. So now that is T1. I'm sorry, T2. That probably confused you because I misspoke. So if the arrows are pointing in the same direction, that's T2. If they're pointing in the opposite direction, that's T1. Does that make sense?
Yeah.
Okay, so then the next important thing to look at is beta, right? So now you have 3 points. You have A, B, and C. So here's C. We'll look at C first. We know that this goes right across the top, and we know it kind of comes down at this diagonal, which means here, oh dear. Let me just do it this way. So we know that it goes across the top and then down at the bottom, right? So here and here. What number in radians describes this? We'll just go. Describes this value. So I have 90 degrees at least, right? That's 90 degrees. And then we know that it has to be in relation to this 45. So we're just going to assume that because this is labeling it 45, this is also 45, right? Because if you look at this, it ends up being like about halfway down this knob, which means that it is 45. So we know that in radians, 90 degrees is pi over 2, right? And then half of that would just be pi over 4. So for point C, beta equals pi over 2 plus pi over 4, which equals 3 pi over 4, right? That's just for point C. So now looking at point B, we know it hits right here and comes off of it right here, So that means that if we're looking at point B, what would our beta be? If it hits here and here. I can either look at it two ways. I can say, here's my y-axis, here's my x-axis, and then these are both halfway through it, which makes this 90, right? Or I can say, well, if I know it comes off on the left side, leaves on the right side, and then touches on the top, leaves on the bottom, that has to be 90. So I would draw it out this way just so they know that you know what you're talking about. But by inspection, this is one of those cases where by inspection would work. You would know that beta equals 90 degrees, which equals pi over 2. Oh, wow. And then for A, you know, it's hitting on right here, coming off right, oh, fuck. Incorrect. Coming off right here. Is that right? No, it's hitting on the side because it's not laying across the top. So it's hitting on this diagonal. So now you're looking at, you know, here's 90. But you're only looking at this little section of it right here. So that would make beta equal to pi over 4. So because beta is being related to the value for mu up here, you're assuming, unless it tells you otherwise, which it won't, you're assuming that these knobs are all made of the same thing and this rope is all made of the same thing. So mu is constant across all of these. So because of that, you can just add all of these together. So you would add the 3 pi over 4 with the pi over 2 with the pi over 4. And that would be your total beta. And then that would go in here for both of these equations. So for that, beta would be, let's see, we have pi over 4, 5 pi over 4, 6 pi over 4, which is 3 pi over 2. And because that'll be constant, because you're not changing where the rope touches in each of these cases, that's constant for both of these equations. So the only thing you're changing from equation to equation here is your T1 and T2. Does that make sense?
Yeah. So then to solve it, we would just
plug in
okay. And then we would add them because like what are we're solving for the range of values. So we would just plug in each one for the min and max. And
yeah, so it would be 6. So again, this is one of those cases where they gave you a mass for this value, right? So you know this equals m. But since that's a mass and you need a weight, you multiply it by 9.81, right? So this is not an unknown. You know this, and you know beta, and you know mu because it gave it to you right here. So the only unknown that you need to look for is your p values. So by solving for your minimum value of p and your maximum value of p, you get that range that it's asking for. So your answer would be somewhere in terms of like p equals whatever number newtons to whatever number newtons to keep it static.
okay.
Does that make sense? A little bit more?
Yes, thank you.
For sure. So again, last call, make sure that you're putting your name in the chat before you leave. And yeah. I will send a video to everyone that's here or that was here at any point today. and I also will send it to the people who gave me a valid excuse to not be here, but it'll be a YouTube link just like it was last time, because I can't send it this, or send a video this long. Outlook won't let me. So it'll just be an upload to YouTube, and it'll be a link. For fairness, please don't send it to people who didn't show up, because that's not cool. I didn't get to sleep in. You didn't get to sleep in. Not cool for them to not be able to sleep in. So that's that.